Welcome to this mathematical survival guide. I'm your teacher Adam Jacobson, and today I thought we'd discuss something that might be quite useful as an economist or indeed as a budding mathematician. That is numbers, and there are many different types of numbers. And I thought we might start with, for example, integers. What are integers? Well, down here I have drawn a number line. Here's 0, there's 1, 2, 3, 4, 5, and here are negative numbers, -1, -2, -3. And the green ones here, those are integers, whole numbers. Right, so is that enough for us as economists to have only integers? Well, maybe we want to say something about the numbers in between these integers. For example, if you want to measure a distance or something. So then it might be so that we may use the rational numbers. And what are those? Well, let's have a look. Rational numbers are numbers that can be written as a ratio. So, can be written as a ratio, for example, A over B. Okay, so let's look at some examples. For example, this one. 3 divided by 2, that's 1.5. That number would be about here. So we can mark 1.5 there. So now there are a few less gaps here, because there are lots of gaps between these integers, between 1 and 2, and 2 and 3, etc. Now there's a little less of gaps. Okay, and we can continue and do more of these rational numbers. For example, 3 divided by 4, that's equal to 0.75, and that is about there. Okay, so now we have seen there's a new class of numbers, and you can see that we can change these ratios, and we can sort of add in a lot of numbers in these gaps. But one thing you must remember when you're talking about rational numbers is that you cannot divide by 0. So, cannot divide by 0, because then such a number is not defined. For example, if you want to calculate the average petrol consumption of your car, and you have consumed 2 liters and the car has driven 0 miles, so liters per miles, you have no idea, right? Because you haven't driven any miles. So that sort of illustrates why you can't divide by 0. Okay, so are there still gaps in between these numbers when we have used up all the rational numbers? Yes, there would still be gaps. There are other numbers that cannot be written as a ratio. So then we look at the irrational numbers. Okay, so what defines them? Well, like I said, they cannot be written as A over B. And can we think of any examples so that we can illustrate what an irrational number is? Well, for example, the square root of 2. If you use a calculator and plug in the square root of 2, you're going to have a very long number. It's going to be something like this. 1.4142, etc., etc., and it goes on and on and on and on. So you can't write it as a ratio, and this is an example of an irrational number. And when we use all these, the integers, that was again 1, 2, 3, 4, and the negative ones, the rational numbers, so they can be written as a ratio. And when we also add the irrational numbers, do we then have any gaps? No, because then we can cover the whole number line. And all these numbers taken together, so the rational plus the irrational equals then the real numbers. So this number line is sometimes called the real number line. So we have a continuous flow of numbers going from the left to the right. And also, going back a bit, we can see that an integer, that is also a rational number, right? Because the integer 2 could, for example, be written 4 divided by 2. So this is also a rational number. Right. So then, now that we know what kind of numbers there are, why did we bother doing this? Why did we bother talking about this number line here? Well, what use can we have of the number line? Well, we can illustrate inequalities. That's something that we, as economists, quite often use, these inequalities. Now, one example of that would be, for example, be A is greater than B. So if some number A is bigger than some number B, that implies that the negative of A is then smaller than the negative of B. In fact, this arrow here is an implication arrow, right? If this is true, then that is true. But we can also see that if this is true, then that is true. So this arrow here can in fact be written as an equivalence arrow. Right. So anyway, so some number A is bigger than B, then the negative correspondence of A is then smaller than the negative correspondence of B. So let us look at one example here. So, for example, let's say that A equals 3 and B equals 2. So, then we see that 3 is indeed greater than 2. So 3 is bigger than 2, it's more to the right. But this is okay in the number line, yeah. And this is equivalent to saying that minus 3 is smaller than minus 2. But hey, why? This number looks bigger than that one. Yes, but let's look at the number line. Minus 3 is here, and minus 2 is there. So the minus 2 is to the right of minus 3. So, in fact, minus 2 is not as small as minus 3. So, this is true. So here you can see that, okay, this number line here is quite useful when we want to illustrate inequalities. And sometimes when you do algebra, it's useful to know that if this is true, then that is true, and vice versa. You will see that later on in the course. Okay, so that was one example of what use you can have of the magical number line. Now, we can also discuss absolute values. What is an absolute value and what sort of use can we have of that? Well, we can think of absolute values as the distance to 0. Okay, 0 is here. So for example, if I go 3 steps to the right, 1, 2, 3, I'm going to be at 3. If I go 3 steps to the left, if you think of this as a map, 1, 2, 3, I'm going to be at minus 3. So there's something that is there is something in common between going 3 steps to the right or 3 steps to the left, even though we end up at minus 3 and or plus 3. That is the distance to 0. So the way you write the absolute value of something is the following. So we have 3 here, and we want to have the absolute value of that. So we draw a line to the left and right of that, and we know that the absolute value of 3, that is 3. Simple. Now then, I said there was something in common between 3 and minus 3 in terms of moving to the right or to the left of 0, if you are thinking of the distance to 0. Well, the absolute value of minus 3, written as this, that is also 3. Yes. So we can think of it in this way. So here I am standing at 0. I go 3 steps to the left, and we see this distance here, that is indeed 3, right? Or I go 3 steps to the left, and this distance is also the absolute value of 3. So this distance is equal to that distance. So that tells you something about what an absolute value is and how it relates to the number line. Okay, now we'll cover 2 possible uses of the number line. And I guess you can see here that there is a third use. Yes, intervals, that can be quite useful to have and to be able to say something about. There are different types of intervals. Now, the first one that we'll discuss is the open interval. Okay, what is that? Well, one example is between 0 and 4. The open interval between 0 and 4. That's the whole distance between 0 and 4. But since it is open, it means that it contains all the numbers between 0 and 4, but not 0 itself and 4 itself. So, let's say that we pick a number between 0 and 4, call it x, and then we can write the open interval in this way. So it's going to be between 0 and 4, right? And x is going to be somewhere in the middle. We know that it is bigger than 0, but it is smaller than 4, because this interval doesn't contain 0 or 4. Okay. So then there is also the closed interval. And let's take the same example between 0 and 4, but let's make it the closed interval. Now that means that you write it like this, with these sort of brackets here. So 0 and 4. This means all the numbers between 0 and 4, including 0 and 4. So we can write this, the interval, let's say that x is a number in this closed interval. You can write it this way. So then you have 0, and you have 4, as before, and you have x in the middle, right? But now we want to say that x is bigger or equal to 0. So you use this sign, and x is smaller or equal to 4. Right, so that means the same interval, but also including 0 and 4. And that, my friends, concludes this class. Thank you very much.